Hi guys! So today we're working on being able to get network and use network to find the speed. I'm going to use problem number 5 from your homework as an example. If you are just looking for the answers, feel free to look at the answer key, but if you want to see where these come from, follow along with me for a few minutes and we'll figure it out. Right. So this problem starts off with an 80-kilogram sled and it's dragged across the floor. We know the applied force is 700. We know initial speed is 1.5. That's going to become important later. And we know the distance it's pulled is 15 meters. The sled has a coefficient of friction of 0.04 against the ground, 0.4 against the ground, and we're going to keep that in mind. So, without further ado, how do we solve a problem like this? Step 1, draw a free body diagram. You know that if I'm asking you to do a free body diagram as step A, that you're going to get prompted to do so. So in this case, we know the normal force goes up. Applied force goes up and to the right. Gravity goes down and friction goes left. So then we would draw ours, all emanating from a single dot, draw the type of force and the direction it's going, and if it's at a non-perpendicular angle, put in the angle, in this case, 30 degrees. Done. One thing you might notice from this problem is my gravitational force arrow is drawn longer than my normal force arrow. That's actually about to come up right now, so let's do this together. We're about to calculate the magnitude of each force on the sled, and some are more obvious than others. For instance, the applied force was literally given to us, so surprise, it's 700 newtons. Magnitude done. The weight, well, that's the mass times gravity of this, so in this case, 80 times 9.8 is going to give us something on the order of like 784 newtons down. 2 out of 4. Done. But now, the tricky part, because we have to go back and remember all the stuff we did in Unit 1. In Unit 1, we worked on how to break vectors up into components. This is a sub-step of Part B. Part B, we're finding the magnitude of all the forces, but what I'm going to need to do in order to solve the magnitude of all the forces is I'm going to need to take my applied force that's currently up and at an angle. 700 newtons is the hypotenuse. 30 degrees is the angle, and I need to break it into its x and y components. Recalling from way back when, the x component of this force, FAX, would be FA, the magnitude of the hypotenuse, cosine 30 degrees, or in this case 700 cos 30. The y component, FAY, would be the magnitude of FA times sine of 30 degrees. This is actually the value we really need in this problem. So FA sine 30 is 700 sine 30, and that's going to give me 350 newtons up. It turns out we don't actually need the x component to solve this problem, but if you wanted to, you could substitute this into your calculator and find it. What I really need is this 350 newtons up, because in order to be in equilibrium in the y direction, the y component of FA plus the normal force have to add up to 784. So, hey, side note, if I have a problem where my applied force pulls up, like the one we just did, or the one we're currently doing, in this problem, that means the normal force pulls up with some magnitude, but so does the y component of the applied force. In this case, the y component of the applied force is 350 newtons. Gravity pulls down at 784. What that means is in cases where the applied force pulls up, the normal force is smaller than the gravitational force. We could write this as something like FAY plus Fn equals Fg, or 350 plus Fn equals 784. So subtracting it to the other side gets our desired normal force of 434 newtons up. But so you see them side by side, that means whenever the applied force pulls up, that means applied force is going to cause the normal force to decrease. When the applied force pulls up, that means the normal force is smaller than gravity because your applied force is helping lift that weight. Alternatively, if you look at problem 4, in problem 4, applied force pushes down. Kristoff is pushing an ice block across the ice, and he pushes down. So his applied force y component would be drawn downward. Gravity would still be pushing down on this ice block, and normal force is actually bigger than gravity in this case. Normal force larger than gravity, and one would write the equation for this as normal force, that's my force that pulls up, is equal to Fay plus Fg. So if you're one of those people that has trouble telling these two situations apart, like problem number 5 versus problem number 4, it's as simple as realizing that one pulls up versus one pushes down. But back to the problem at hand. So we figured out the normal force. We figured out the applied force. We figured out the gravity force. That just leaves the friction force. And by all means, the friction force is not bad because that one is on your equation sheet. Don't forget to look there. It would be under unit 2 is the equation for friction force. Friction force is going to be mu times the normal force. Mu is going to be 0.4. Normal force is that 434. And that's where I get the friction force of 173.6 newtons left. So let's go over the steps. We drew the original free body diagram. That was part A, and it was prompted in the problem. Part B, we find the magnitude of all the forces. This might involve breaking forces into components, using equations from previous units like weight is equal to mg, or that mu is equal to, friction is equal to mu times Fn. Now let's do the work. Work is part C. The work done by each of the 4 forces is going to be calculated in one of 3 ways. I could do Fd cosine theta. I could do the area under a force distance curve. Or we can do the change in energy. We're going to do the force distance cosine theta equation though, because I know that I was prompted to. Meaning, I saw that I have forces. I know what they are. I know the angles because I drew the free body diagram. This is the equation I would use if I have a free body diagram with known forces. And how we use that equation is we draw each of the forces out. So in this case, normal force pushes up, gravity pushes down. Applied force goes up and to the right, friction force goes left. I would draw each of my 4 forces. So normal, gravity, friction, applied, and then the distance it travels. In this case was 15 meters to the right. So I'll put in my 15 meters to the right for all 4 of these forces. Then, now that I have my force drawn and distance drawn, I can get my angle. This angle would be 90 degrees. This angle would be 90 degrees. These two are going to do 0 work because the force is not in the same direction as the distance. If you remember the work and power song, which I'm sure you've tried to forget the work and power song, work is only done on an object if the force moves the object in the same direction. See how I didn't sing the answer there? Isn't that nice? If it's not moving in the same direction, this is Fd cosine 90, which gives me 0 as the work done for both the normal force and the force of gravity. The applied force would be Fd cosine theta, where F is going to be the magnitude of the applied force, D is going to be 15, and theta is going to be 30 degrees in this case. So it would be 700 times 15 cosine 30, and that's where I get the 9,093 joules for the work done by the applied force. This is positive because it's adding energy to the system. Finally, friction. We're probably not going to do in class a situation where friction does positive work, but it is totally possible. In this case, friction does negative work because the angle defined is 180 degrees between the distance and the force. So I would take my 173.6 newtons to the left times 15, cosine 180, and the work done by friction is negative because it's removing energy from the system. Not bad, right? So that means part D, find the net work, is actually pretty straightforward. Remember that net means sum. I am literally going to take the sum of 0 plus 9,000 plus 2,000. Oh, I can totally do that. So my net work means sum up the work done by each force. Take gravity's contribution, normal forces contribution, the applied forces, and friction forces, and I'm going to add them all up. 0, 0, 9,093 minus 2,000. Well, technically it's plus a negative, but you know what I mean. Minus 2,700. That means my net work is some positive number. It is 6,393 joules, and positive means it added energy to the system. So what type of energy could this possibly add? Well, let's go back to your original picture. Is our sled dragging friend here pushing the sled into a spring? No. Pushing the sled uphill? No. That means the only type of energy it could possibly be adding to the system is kinetic. Now, I was kind of mean in this problem. When we're going to draw the initial kinetic, potential, gravity, and spring, there's obviously no gravity to start because it's on the ground. Obviously no spring, but I was a little bit tricky on the kinetic energy initial because I don't know if you remember, I mentioned the speed initial is 1.5 meters per second. Hey, that gives the sled like a little tiny incy-wincy bit of kinetic energy to start. So I'm going to find its kinetic energy with 1/2 mv squared. So that's 40 times 2.25, and that gives me 90 joules of initial kinetic energy. But on the scale that I'm going to draw, 90 is pretty insignificant compared to the 6,393 I'm going to add for work. So we're going to keep in mind that it's there. It is non-zero, but it's really tiny. Okay? So think about this in terms of what sort of energy you're adding to the bar graph. You start with 90 joules of energy. Then, my person who is outside my system does work external. And they do 6,393 joules of work. And that means my kinetic energy in the final picture is 6,483. Look at that math in my head. 6,483 joules of kinetic energy at the end, because the kinetic energy at the end is equal to the work you did plus how much you started with. The work adds kinetic energy to the system because it didn't push it uphill and it didn't push it into a spring. Ta-da! So final velocity of the sled then. If you know there's 6,483 joules of kinetic energy, I can find the missing velocity. Step F. Kinetic energy is 1/2 mv squared. And pretty much in this unit, anytime you are asked for a speed, write down this equation. Put it down on your test. Put it down on your paper, because how to find a speed when we're dealing with energy is literally only this equation. So, multiply by 40, I multiply out and get 40 on the right. I'm going to divide by 40 on both sides. Don't get a square root happy and try to square root before you divide. So this gets me my 162 is equal to v squared. So that v is finally equal to 12.73 meters per second. So, from start to finish, this problem requires you to draw a free body diagram, calculate the magnitude of forces using the weight equation, the friction equation, components, and being able to identify whether forces pull up versus pull down. This problem requires you to be able to calculate work using the FD cosine theta by identifying the angle between the force and distance. Finally, figure out the network, which adds energy to the system, and use the energy to find a missing speed or height or compression or mass. If it's one of the variables that shows up in an energy equation like M, V, X, K, H, it's fair game for a problem like this. So, best of luck. I will see you soon.